Okay, welcome to today's class. We're talking about decision analysis. So, what is decision analysis? When we talk about decision analysis, we are just trying to make decision in regards to two events. Okay, for example, in a particular company, you want to produce product A and product B. So, the decision to produce either product A or product B is depending on different factors. So when you consider this factor, then you can now decide on which one you're going to pick. So decision analysis is majorly based on probability. So in manufacturing, in manufacturing technology or production engineering, so we deal with a lot of decision to make about producing any products. So that is how decision analysis comes about, and it helps us to in development, in research. So we use decision analysis a lot. All right, so this is where decision analysis. We have two types of decisions. We have single decision, then we have multi decision. So single decision is just talking about you having just one, you know, you having one thing to take, like your intake is just going to be one. So for my textbook here, I have the single decision to be when you are limited to a single decision taken over one period of time because the payoff, state of nature, causes of action, and probability associated with it is just not subject to change. When it comes to multi-decision, the payoff, the state of action, all those parameters, they tends to change on the long run. So that is that about single decision and multi-decision. So I'll just go to calculation today. So the question will be displayed. It said we are given the following estimate concerning a research and development program. So the decision is given the table. We are underdeveloped. The probability of decision DI, which is D1, given research that is you are to the probability that you are to develop is 0.5, given that you are given a research, and the probability that you are not to develop given research is 0.5 as well. So it is 50-50. And we are given number of outcome that we have outcome 1, 2, 3 for both develop and not to develop. They also are given the probability of outcome xi given di. We are given all the parameters there. Then we're also given the payoff of individual states, which is state 1, state 2, state 3. So you can see states, I call some states. Yes, so 1, 2, 3 are states. That is, they tend to change, right? They determines the action we're going to take. Yeah. So we have to construct and evaluate the decision diagram for the stated data. Show your workings for evaluation. So in solving this kind of problem, if you want to solve it, you just start from your zero decision. So we are given there that to develop so these are states. So say 1, this is 2. So the probability of develop here, probability to develop, which is di, probability to develop, which is d1 when there is research is 0.5. Probability not to develop when the research is there already is 0.5 as well. So we are given 3 states. State 1, then states, another state here. So there is another state here. So we are having 3 states for either to develop or not to develop. So for this develop, so let me call this 3, 4, 5, 6, 7, 8. Now we have to develop. So the probability of an outcome here, PXI, for develop is equals to 0.6. Probability of, which is px1, px2 to develop is 0.3. Probability of an outcome 3 to develop is equals to 0.1. You can see if you sum it up, it was equals to 1, because when you talk about probability, about a posteriori probability, so the probability can either be 1 or 0, so it cannot go beyond 0 and 1. So, and if you sum these probabilities up, it was equals to 1. Then the next thing is the probability of an outcome 1 when not to develop, it is 0. You can see that when not to develop, D2. Probability of an outcome 2 when not to develop is equals to 0.0. The probability of an outcome 3 when not to develop is equals to 1.0. So if you sum everything together, you're going to get 1 as well. So what's going to happen here is that we're going to determine the conditional probability between this and this. So we're going to determine the probability. So how do we get that? So I can call this place probability A. So I'll call it perhaps P. Actually, I need more thing here, you know. So to determine the probability here is just like saying 0.5 times 0.6, which give me what? I think that is 0.30. Now for the condition 4, for this point 1 to 4, it's gonna be so it's gonna be what? Can you tell me if you say 0.5 times 0.3, you are right. So this is gonna give me what? 0.15. And tell me this. So if you say 0.5 and 0.1, then you are actually correct. So this is going to give me 0.05. Yeah. So, and for this, now we are done with develop. So we are under not develop now. So this is develop. And this is not to develop. So if you look at this, if you want to get the probability under this condition, you're going to be this is 0.5 times 0.0, which is what? 0.0. And this one also is 0.5 times 0.00, that is 0.0. And this is 0.5 times 1, 0.5 times 1.0, which is what? 0.5. So these are the probability. So actually the board is not that long. If not, I should have continued here. So please, this line I'm going to draw here now is the continuation of that front. So bear with me for now. So I'm just going to put 3, 4, 5, 6, 7, 8. So adding this is very long, then I should continue on that page. So the next thing we're going to get here is the payoff. The payoff. The individual payoff for all these states is, so okay, we are giving in thousands. The payoff as in 1,000. We are giving the table, and the payoff value of outcome xi is in 1,000. So the n you see there, it means is in 1,000s. So in naira. So the payoff for condition 3 is 600. Then the next one is minus 100. So I think this repeats itself. This is also 600. I think so. 600 minus 100, then 0. So the next thing we're going to do is that we're now going to find the payoff. So I'll call this one P. So let me call this one L. Payoff. So the payoff for the conditional probability, you know, this is just the payoff for the outcome itself. So these are the payoff for the outcome, but the payoff for the conditional probability is you multiplying this with the probability you get from this point. So 600 times 0.30 is going to give us, I think that's going to give us 180. Then minus 100 times this is going to give us minus 15. Then this is going to give us 0 times 0.05, give us 0. Then 600 and 0, then that is 0. 100 times 0, that is 0. So this also is 0. So we can see that we have this payoff for develop. This is for develop, don't forget. I just use this line so that I can know the difference. This is for develop and this is for not develop. So we have to find the total. Total for develop, like total payoff for develop is equals to 180 plus minus 15 plus 0, which is equals to 165. Now this 165, you have to convert it back to the naira. So which is what? 165,000 naira, because I've told you initially that this is in thousands of naira. Therefore, total for do not develop. So the total for do not develop is 0 plus 0 plus 0. You know, naught plus naught is C naught. So we can see that the total payoff for do not disturb is 0, and the total payoff for to develop is 165,000 naira. So it simply shows that since the total payoff for develop is more than the total payoff for do not develop, then it is advisable to go for development and do the research for the projects. So that's just the decision analysis that using decision tree. So for decision analysis, we have different methods. We have the method of decision tree. So what I've just done now is decision tree method. Then we also have what they call Markovian theory for solving decision analysis. Then we also have Bayes, so Bayes process for solving decision analysis. Thank you. We continue on the decision analysis. So the last time we discussed about decision tree. So this time around we're going to be talking about Markovian. So we are still under decision analysis. Markovian principle for solving decision analysis. So one of the major aim of Markovian principle is that you need to get your maximum return. So the aim and the objective is to maximize return. That is the aim of Markovian. So the difference between Markovian and Bayes is that Markovian looks for maximum return, while Bayes is used to minimize the cost of production, or to minimize investments. So the amount you are putting in investment, you want to minimize, you use Bayes. But if you are looking for return, like the outcome or profit, you use Markovian. So I hope you get the difference. So today we're going to be talking about Markovian. So we are given the decision function. This is a function we call it objective function. So the objective function, I being the state, then K being the condition we are considering, is equals to summation from J equals 1 to M, then probability function along the various decision. So Ij, then we have the return Ij under this condition, So this is what Markov really stated. So this is the objective function. To get the objective function, we are going to use this formula. Then we are going to use backward recursive function to determine the value at different stage. So we have stage, we also have states. So note I is state, then we also have the stage. To determine the stage, we are going to use backward recursive function. Now when you start applying those functions, you understand all these things, but you have to know all this formula. So the first thing we have to know is Fn. So Fn is the maximum. You know, I told you that Markov is about maximum. The maximum of this condition K, the maximum of Vi to K. So this is your function, the optimal function at a particular stage. Then I call this one what? Optimal function at a particular stage. Then you know it is an iterative method. So the next stage, to determine the next stage, it will be Fn, which is equal to the max of Vi to K plus summation of J from I to M, then your probability, which is Pij, multiply by the function of the previous stage, n plus 1, then high. N plus 1 high. So this is the function itself. So our n is equals to 1, 2 to capital N. 1, 2 to capital N. So n continue. So let me just go over it again. This is our objective function, and the aim is that to get an optimal value. To get an optimal value, I told you that Markovian deals with what? Maximum. It maximizes the objective function. So we find the max of this objective function. After you find the max, then for you to iterate it, because you are going to iterate to your desired solution, where you are going to get the maximum solution. Then for you to get the optimal solution of the next stage, you're going to use Fn equals max of K, max to K of Vik plus summation from J equals 1 to M, then the probability at this position Ij, then function F plus, and this is optimal function of the previous stage you got, high. So this is just what everything about Markovian. So if you can know all this formula, then you are good to go. So we can go to the example now and apply this. We're given this data. The probability for a farmer. Now, the first condition is that the farmer should not apply what's it called now? Fertilizer. So the farmer should not apply fertilizer. So if the farmer does not apply fertilizer, what will happen? So we have the states. So you have the states to be like this. The probability is given in 3 by 3, 0.2, 0.5, 0.3, then 0, 0.5, 0.5, 0, 0, 1, 0, 0, 1. Then the return that we're able to get from this particular stage, whereby the farmer does not apply fertilizer, the return is given as, let's say, a matrix 763 051 00 minus 1. So now let me interpret this. So the meaning of this is just like, this is the first year, this is the second year, this is the third year, and this states the state of a very good soil, a fair soil, and a poor soil. So we've been told that in the first year, and you're not applying fertilizer now, on a good soil, your return is going to be this. So on a poor soil, the return will reduce, you are expecting that. Then on the first soil, rather, you have like 6 return. Then on a poor soil, you are going to have 3 return. But in the second year, see what is happening. Your return, you just have 0 return. But when you get to the fair soil, perhaps in the second year now, the soil is fair, right? And it can still do well. So we are getting this 5 return. And at this point, you are getting just 1 return. Then in the third year, there's no return at all in the poor and the fair soil. Then what the investment is still the same thing as what you got. That is the meaning of this. Then for this, it means you are having a deficit of -1 because of the soil is very poor. Instead of you having the soil to generate crops, then you are now having deficits. So now the second condition is when you apply fertilizer, which is P2. This application of fertilizer, the probability is Pij to 2, right? Equals, so I'm just going to put the probability on the board. 0.3, 0.6, 0.1, 0.1, 0.6, 0.3, 0.05, 0.4, 0.55. So the return is equals to, so the return is equals to, I'm going to put the return on the board. 65 minus 1, 740, 63 minus 2. So this is the return. What is the aim? So the aim to compute the values of VIK for all I. What is I? I is the state. For all I, given that fertilizer is used while the system is in stage 2 and 3, which is, with the meaning of stage 2 and 3, fair and poor respectively. Otherwise, no fertilizer is used. So this is our aim, to compute the values of VIK, the objective function for all I, given that fertilizer is used, then fertilizer is not used. So that is the aim. So I'm going to rub off the board so that we start solving. So to solve this question, remember that our VIK, for write out its formula so that it can guide you, is summation, then I from 1 to m of the probability of individual cases you are considering, then the return ij k, then for the objective function fn at each stage is the max of VIK. So at each stage, now let me leave the each stage first. Then after we have solved for this one, stage 3, then we will now proceed. Now, how do I know that it's stage 3? In the question, you'll be given that, yes, you can see the probability I gave you, 1, 2, 3. So we are given like 3 years. So our n is going to be 3. So n is going to be 3 because we are considering what for 3 years. So we start from it. I told you is a backward recursive method. So we are going to be applying backward recursive method here. So we start from stage 3, then we'll get back to stage 1. So for stage 3, we are going to determine the objective for each value. The objective for each value. So how do you determine that? This is the formula already. So I want you to go back to the table, like the probability I gave you and the return. So I want you to go back there, so you'll be able to determine the objective function for each state. So now I want to consider for k equals 1. So do you want to tell me, do you remember what k equals 1 simply means? K equals 1 simply means what? It simply means that the farmer should not apply fertilizer. So that is the meaning of k equals 1. So if the farmer is not going to apply fertilizer, what's going to happen? So we're going to consider it for each state. So when I equals 1, that is good soil, I is 2, fair soil, I is 3. That is what? Poor soil. So for V1 of 1, so VI, that is a good soil, is equals to, so I want you to go back to the probability. So I'm not going to write the probability up, but please consider it as I've written it down. You will see everything there. So the probability for V1 is going to be 0.2 times 7. I think there is a necessity for me to write it out. So let me write it out. Now we're going to determine the objective function for K equals 1. So these are the probability and the return respectively. So we are going to determine for each state. So K, the objective function V1, that is state 1 at position K equals 1 is equals to. Now how do you get that? We want to determine V for 1, 1. So that will be this times this plus this times this plus this times this. Just like position 1, 1 multiplied by position 1, 1. Position 1, 2 multiplied by position 1, 2. Position 1, 3 multiplied by position 1, 3. So that will be equals to 0.2 times 5, times 7 plus 0.5 times 6 plus 0.3 times 3. So at the end of the day, when you multiply this thing together, so I'm going to do it and write out the value. So we'll be getting 5.3. So for V21, that is at the state of a first soil, what do you have? This times this, which is 0, right? Plus this times this, we're going to give us 2.5. Then this times this will give us 0.5. So this is going to give us 3. So at position V31, that is at the poor state, what are going to have? 0, 0, 0 minus 1. So it's going to give us what? Minus 1. Because 0 times 0, 0 times 0, then 1 times minus 1 give us minus 1. So we're going to do it for, what's it called? V, when K is equals to 2, that is, the farmer should apply fertilizer. So the farmer should apply fertilizer at this position. So the same thing, I've given you the probability from initial. I can't write it out now. Then I've given you the return as well. So at the end of the day, when you multiply it together, for V12 is equals to, so let me put the value up, 4.7, then V22 is equals to 3.1, V32 is equals to 0.4. So that is the what's it called now? The objective function for each state at stage 3. Now I'm going to populate this table. So after you have determined your objective function at each state for K equals 1 and K equals 2, so you have to draw this table. It's on this table you're going to determine your optimal value. That is, at what state is it to apply fertilizer or not to apply fertilizer. So when K equals 1, so what we're having there is, so let me populate this, that is V11. For V11, what do you have? We are going to have 5.3. For V21, we're going to have 3, then minus 1. Then for when K equals 2, for V, we have solved it already. So for V12, we're going to have 4.7. For V22, we're going to have 3.1. Then for V32, we're going to have 0.4. So now, you can see what I write here. I say optimal solution. So optimal solution simply means, the objective function is the maximum between V, I, K. So what is the maximum between under state 1? That is when the soil is good. So which one are we to adopt? That's which one is bigger? 5.3, right? So it simply means that this point is going to be 5.3. Now it is very true, because at initial stage, when the soil is very good, when you apply something like you plant there, your soil is going to perform well. So which is very true. Then at this point, which decision should we go for? Decision of K equals 1, Abi. So we go for decision 1. Then which one is at a state where the soil is poor, which is state 2? Which one are you going for? 3.1, which is the bigger one. So what's going to be the solution? The K, I say that is the optimum K. So if you say K equals 2, then you are right, because we are taking K equals 2. So which one is bigger between minus 1 and 0.4? If you say 0.4, then you are right, because 0.4 is bigger than minus 1. Then which decision are we taking? We are taking decision 2. So what does this simply mean? It simply means that when the soil is good, yes, when the soil is good, please, you don't need to apply fertilizer. But when the soil is fair and when the soil is poor, it is advisable that you should what? Apply fertilizer. Good. We are going to get to stage 2. So what I'm going to do here, we are going to iterate using backward recursive method. So what is the formula? So Fn equals, that's going to be max of K from Vik plus summation of I equals 1 to M, the probability Ij, K, then Fn plus 1 I. So this is it. Now since we are under stage 2, that is N equals what? 2. So this one will be what? F2 equals max of K, then what? I'm going to have Vik plus M sigma I to 1 from I equals 1 to M, probability of Ij, K, then 2 plus 1 is going to give us 3. Remember that F3 is what we got at that optimum solution table, then high. So now I want to determine F2 for each state under K equals 1 and K equals 2. So when K is equals 1, then let's go. F2 of 1. When K equals 1, F2 of 1, I can also put 1 here to just denote K, right? So F2 of 1 will now be equals to, consider this formula. At the end of the day, when we want to find the general formula, the general optimum value, that is when we use max. So Vik. So Vik, I'm going to write the Vik here for us to see. So the Vi of 1. The Vi of 1, that is what we got when we were solving it, and that is still the same thing as 5.3 for 1, 3, then minus 1. Then we also have the Vi of 2, which was 4.7, 3.1, 0.4. This one, they are not changing. Then the optimum value for F of 3. So I'm going to write it here. We take 5.3, 3.1, 0.4. So let's go. So what I'm going to consider, I'm going to take for this one first. So that will be 5.3 plus the probability, the individual probability for 1. You know the probability already. I don't need to write it. If adding the body is very big, I would have written it out. So the probability is there already, but I'm going to copy it from my book so that I won't waste much time. So it's going to be the same thing we did, 0.2, which is the first probability. 0.2 times, please take note, times what? Times 5.3. Now we are not using, we are using F3. So this is I1, that is 1, this is 2, this is 3. So F3 of 1, this is it. So that is 0.2 times 5.3, then plus, the next probability is 0.5. Open bracket, what? 3.1 plus 0. That's 0.2.5, because that's 0.3 times 0.4 times 0.4. So this is for F2 of 1. So at the end of the day, when you sum this one together, so I'm going to write the answer so that we won't waste much time. So it's going to give us 8.03. 8.03. So the next thing is that we're going to go to when I equals 2. So F2, when K equals 1, then of 2. Now this time around, 5.2 is for V1K. This is V11. So for V21 is what? 3. So that is 3 plus. So the probability, the expected probability is 0, 0.5, 0.5. So that is 0.0 open bracket. Now this one, they remain constant. Just take note of it. This one remain constant throughout for it. So that will be 5.3 plus 0.5, then 3.1 plus 0.5, then 0.4 rather. So at the end of the day, what you're going to be having is 4.75. 4.75. That's what we're going to be having at the end of the day for F2 1 of 2. Then F2 1 of 3 will now be, now take a look, what is it? If you say it is 0.4, then you are correct. 0.4 plus, remember that the probability is 0, 0, 0, then plus 1. So that's going to be what? 0 open bracket what? 5.3 plus 0 open bracket 3.1 plus 1 open bracket 0.4. So at the end of the day, we're going to get to I think 0.8. So 0. Yeah, that should be 0.8. Because 0.4 plus 0.4 here, we're going to give us 0.8. So we have determined F1, F2, F3. So this is for k equals 1. Now let us determine for k equals 2. So please, I'm going to do for k equals 2 up here so that we're going to see what we are doing together. K equals 2. So we're going to start again. F2 1 of 2, which equals to, now take notes. We are not considering this point. We have what? 4.7 plus, so what are the probability? We have 0.3, 0.6, 0.1. So 0.3 open brackets. Now remember, this thing remain constant. 5.3 plus 0.6 open bracket, there 3.1, good. 3.1 plus 0.1 open bracket 0.4. So at the end of the day, when you multiply this and sum it together, so we're going to be having 8.19. So I'm doing this because I want to save time. So we are not here to be testing how you know how to calculate. No, we are considering about maximization, not your calculation skills. So you can use calculator to determine this. So for F2 2 of 2, which is equals to, now you come to this point, 3.1 plus, so let me get the probability, 0.1, 0.6, 0.3. So 0.1, then this thing remain constant, plus 0.6, this remain constant, there plus 0.3, this remain constant. So at the end of the day, we're going to be getting 5.61, 5.61. Then for F2 2 of 3, which is this last one, 0.4 plus 0.05, then 5.3 plus 0.043.1 plus 0.55, then 0.4. So at the end of the day, you see that this will give us, this is going to give us 2.13. 2.13. So we have determined all this value for respective function at stage 2. So the next thing is that we're going to draw the table again. So we'll be able to determine our optimum solution. This is an iterative method, by the way. So we follow a backward recursive method. So let's draw the table. I've calculated everything. So we want to populate the table. So for stage 2, we say this point is 8.03. Then this place is 4.75. This place is minus 0.6. Please correct that from your calculation. Like there is a point there, I wrote 1 instead of minus 1. So it should be minus 1 plus 0.4. Not 0, not 1, not 0.4 times what? 0.4. It is minus 1 plus 0.4, which is going to give us minus 0.6 for this aspect. Then we have 8.19. Please, you just need to use your calculator to confirm all these figures. You get that? But I'm very sure of it that this one is minus 0.6. So 5.61, 2.13, 8.19. Then now, how do you get 8.19? Which one is bigger between this and this? Is 8.19. So our decision here is what? 2. Which one is bigger? Because this one is 5.61. Which one is bigger between minus 0.6 and 2.13? Is 2.13. So we can say that the decision we are picking between K1 and K2 is always what? 2, 2. So what is the interpretation of this? It simply means that in the second year, that after you have used this farmland in the first year, for you to get maximum output That is, if you want to increase your output and increase your return, you have to apply fertilizer as a farmer. So it is advisable that you apply fertilizer. Either the soil is good, fair, or poor. You know, from initial, I said N equals what? N equals 3, right? So we started from stage 3, stage 2. So this is the last stage, which is stage 1. So we want to find the final, iteration. So how do we get this? For stage 1, so it's not going to be F1. So F1 of I is equals to, now what is going to be? Max of K, VI K, plus summation I equals 1 to M, probability of Ij, the probability Ij of K, then the function, the previous function we get, which was what? F2 I. So this is the formula we're adopting. So how do you go about this? So it's very simple, just say K equals 1, then you start the iteration. So the same thing we used the other time. So let me put it here so that you'll be able to see. So V1, VI1, then V2, okay, VI2. So this is 5.3. Let me get that. I can't remember fund. 5.3, 3 minus 1, 4.7, 3.1, 0.4. So the optimal solution we got the other time was 8.19, 5.61, then 2.13. So I'm just writing this out so that I'll be able to see it. Not be opening your book up and down. So K equals 1. For K equals 1, so what's going to do now is that F1 1 of 1. So F1 1 of 1. So what's going to be F1 1 of 1? It's going to be the that will be 5.3 plus the probability. So probability is still the same thing. So just go back to your book and check the probability and write it out. So I'm going to check my own book to get the probability. So 0.2, open brackets. So 5. No, this is going to be 5.3. Open bracket, this optimal solution we got 8.19 plus 0.5, open bracket, 5.61 plus 0.3, open bracket, 2.13. 2.13. So at the end of the day, when you sum this one together, so what you'll be getting is going to be 10.74. Then for F1, so this is going to be F11 of 2. So which is going to be giving us 3 plus, so the same probability again, 0 open bracket 8.19 plus 0.5 open bracket 5.61 plus 0.5 open bracket 2.13. So what we get at the end of the day is going to be 7.92. Sorry. So this should be 10.38, and this should be 6.89. Please correct it from your notes. So when you multiply this and sum it together, you're going to get 10.38, and you'll be 6.89. Then for F1 1 of 3, F1 1 of 3 will be the last thing there, which is minus 1, then plus, so the probability for this is 0.001. So that is 0 open bracket 8.19 plus 0 open bracket 5.61 plus 1 open bracket 2.13. So at the end of the day, what you're going to be getting is 1.13. So 1.13 for this. So we have gotten the function for stage 1, 2, and 3. So K equals 2. When K equals 2, so that is F1 2 of 1. So the same process, the same thing I've been doing. Then I'll just populate the value for you. So we have what? 10.74 F1 2 of 2 is equals to 7.92. F1 2 of 3 is equals to 4.23. So take note of that. So we have gotten all the values. So the same process we carried here. The only thing you just do is change the probability, then change this value. So you get your F1, F of 1, F of 2, F of 3. So now we have gotten this, then let us draw the table. So what's going to be our optimum value here? Between this and this one is greater. 10.74 is greater. This one is greater. 7.92 is greater. Between this and this one, 4.23 is greater. So what is going to be your decision? So for everything, we can see that we are picking decision 2, 2, 2. So what is the meaning of this? Let me interpret it for you. It means that in the third year, you have used the soil in the first year, the second year. So in the third year, irrespective of the nature of the soil, that irrespective of the state of the system, you are to what? Select option 2, that is K equals 2. And what is the meaning? You have to always apply fertilizer if you are looking for what? Optimum solution. That is, if you want your return to be maximum, you want to increase your outputs, so you have to what? Apply fertilizer. So what is the our aim is to determine VIK. So what is going to be for application of fertilizer? We can see that you can only apply fertilizer. You can only leave the soil without application of fertilizer when you're in the first year and the soil is good. And another one you can also do, I think that is the only place you can do it, when you're in the first year and the soil is good. But for second year and third year, it's advisable that you must apply fertilizer. So MARKOVIAN has helped us to make decisions on how the farmer should, utilize his farmland. Thank you.